Okay, let me start to review what we've learned in the last lecture. Okay. The key word that was really emphasized in the lecture was, what was it? Okay, impedance, right? Impedance. So highlight of last lecture is impedance. In other words, we recognize that impedance really dominates the waves that propagate along string, and certainly that indicates later on impedance would dominate or determine the wave propagation in general 3D acoustic case too. Okay? So let's start with 1.5. That has to do with forced response of a string. Where we talk about here driving point impedance. Okay. Suppose the following two situations. Okay. I am oscillating the string with the magnitude of y with the frequency omega. Okay. If there is no boundary, then what we can expect is that the wave will propagate from here to the direction over there. Okay? And what if we draw the string at one end, but if the string is terminated over here, I suppose this is length L. And what it can guess is what we feel at x equals 0 would be different. Okay. The reason why we propose to study these two extreme cases is the general case. For example, if the boundary is not rigid and nor infinite boundary condition, but it has a certain spring mass system in general, then what we feel over here would be somewhat in between, right? So that really motivated us to study these two extreme cases. Okay, so let's study this one first. From the previous lecture, we know that in this case, the displacement in y direction, of course, originates starting over here, and I'm measuring the displacement of string using y coordinate. And that will be expressed as g x minus ct, and I'll put s over here to emphasize this is the wave speed of propagation along string. Okay. And the g is the shape of a wave. As this mathematical expression certainly completely expresses what's going on over here. Okay. And then the displacement at x, that is when x equals 0, t, is g minus CST. Just a consequence of this functional relation with x. And because we assume that we are exciting the boundary at x equals 0 with the displacement y exponential j omega t, I can write g minus CST is equal to y exponential j omega t. Okay? This is sort of a straight way. I mean, there is no other alternative. We just followed the definition of mathematics. I mean, functional relation of mathematics. Then I can say that, hey, this is a function of omega, and this is function of minus CST. Therefore, we have to make these two functions, I mean, these two functions must have the same form, right? Therefore, we can write this as y exponential CST, right? But this has to be same as this. To make same, I should put some constant over here, k. Okay, and this is minus, so I put the minus. Okay, sorry, right again over here, minus CST and k, and I need j. Okay, did I? Sorry, I like to put the minus over here. I will explain later what the difference between minus j omega t and plus j omega t, but I want to put minus over there. Then this has to be minus. So we can assume over here g alpha has to be equal y exponential plus jk alpha, and this is simply the functional relation. The independent variable is alpha, so I put alpha over here to be x minus CST without loss of generality, because I can use any alpha. So I have this. Okay, that's the possible wave I can have on this positive x-axis. Okay. Then let's look at the impedance, mechanical impedance at x equals 0, that is defined as the force acting at x equals 0 with respect to velocity at x equals 0.